It's a great pleasure to be here to talk about this work. I would say that to kind of lead off this session, I'm providing a talk of more about an application of some of the interesting mathematics that are relevant to this session. I will highlight some technologies that subsequent speakers will discuss, but this just kind of shows how some of these interesting mathematical ideas actually have practical application. So with that, I will get started. So I first of all want to thank a couple of my co-authors, as well as many other people on this project. So first of all, the project has many folks and stakeholders. The project I'm talking about today is led by Professor Sandy Pentland of MIT and his team, as well as a number of folks on my team. And this project has a wide range of commercial and academic partners, which we're really excited to have, who make extraordinary contributions to this project. And a few of them are highlighted here with their logos and such on the right. So let me just give you an overview of kind of the problem we're trying to solve. It is how to protect the internet. And, we need better ways to observe the internet and apply new AI methods to do that. We need very large data sets in order to be able to do the math and science to figure this out. So to help orient our audience, a picture on the right is essentially of the entire internet. And wherever you're on the internet, you can, or any network for that matter, you can create this traffic matrix picture on the right, where the rows are the sources, and the columns are the destinations, and a point in this matrix represent communication or interaction between these different spaces. So this can be viewed as a giant matrix. And then through the power of matrix transformation, if there's some block of sources and destinations that you consider kind of your space that you want to protect, and some other block that's considered where you're trying to protect yourself from, you can divide this space up into these three regions, sort of what we call blue space, gray space, which is everybody else, and red space where adversaries may be trying to attack you. And one of the things that will become very important in this talk is the fact that you'll see this word anonymized appear. So one of the key things, particularly with respect to this point here of getting data, is that when you operate in this application area, privacy has to be the first and last words out of your mouth. So every single algorithm, all the mathematics we talk about here, is designed to assume that all the data has been anonymized. So that's kind of a unique aspect of the work here. Is we're one of the few projects that really just assumes all data we get is anonymized. And because of that, people give us a lot of data. They like that a lot. They like the fact that the data can be anonymized and that we can still do very interesting things with it. So there's a whole hierarchy of data here in this space. At the lowest level, every single thing on the internet is broken up into little tiny things called packets. So this entire Zoom call is been broken up into millions and millions of little packets. And at the top, there's a sort of a pyramid community, right? So we can imagine the SIAM community is at the top of these communications right now. And then there's layers in between. Packets are assembled into flows. Flows can be assembled into various types of transactions. Then you can have kind of movements of people and social groups. And so one of the things we want to do is we want to do analysis of each of these layers, but also do analysis across the layers Again, that's another thing that's kind of cool about this project, is the fact that we do a lot of anonymize within layer analysis and anonymize across layer analysis, and developing these AI methods that work across this entire space is something we'll talk about today. There's basically two lines of effort in this project. I'm mostly going to be talking about this bottom line, which is called Cipher, which is essentially the how do we collect and deal with the enormous volumes. Hypersparse matrix theory is going to play a huge role in this here. So this is something we call the Cipher project, which is really sort of how do you do anonymized hypersparse matrix sensing. And then at the top here is a thing we call NetSage, which is how do you effectively take data from different places and kind of analysis from different places and merge them together to create a coherent picture so that you can do things about it. Part of the reason that I say the word hypersparse all the time is because when you're dealing with the internet, at a minimum, the number of rows and columns are each 4 billion, right? And it can also be much, much, much larger than that. So these are 4 billion by 4 billion matrices that generally at any moment in time don't have a lot of non-zero entries, and so they fall well into what we would traditionally call the hypersparse regime. So what are we trying to accomplish here? So for those of you who are new to the field of cybersecurity, let me briefly, now that we've established this picture, it makes it fairly easy to explain what most cyber attacks look like. So your adversary, they plan in their red space, they then stage their attack in gray space. They rarely attack directly from their red space. Once they're in gray space, they infiltrate the blue space, i.e., they get someone to click on the wrong web page, or they open the wrong attachment, and then they're inside the blue space. They then what's called move laterally. So they start, once they're in blue space, they start trying to infect other computers. Eventually, you might have software installed on computers, virus scanners, something else that detects that. And then you begin what's called the cleansing process. Oh, you discover that there's been a compromise and you cleanse. And of course, by the time you've cleansed, this is happening elsewhere in blue space. It's sort of a never-ending game of whack-a-mole. So one of the things we want to do is move towards what we call proactive cyber. So we're going to have much better sensing of our own networks. And then we're going to be doing this as a community. So this will be our blue space. But our blue space is someone else's forward network sensor, and someone else's blue space is our forward network sensor. So these pluses out here in gray space, working as a community, allow us to detect adversarial activity in the staging stage, which makes this a lot easier a problem to deal with. So, and again, the key breakthroughs have just been really some mathematics and software technology, high performance graph technology that allow us to actually realistically do this in an effective manner. So for this audience, hopefully the mathematics here is fairly straightforward, but for many people in the cybersecurity community, thinking about the entire internet as a big giant matrix is a bit new. So we actually have a video game that we put together. I can share the link to that at some point later, but it's just a video game that people can play where they can deal with sort of the internet now is just like 10 computers. There's a red space, there's a blue space. These palettes of packets sort of indicate the communication, and then the user gets quizzed about so which stage of this. So this is the planning stage. We have packets in red space, and then the staging stage, we have red to gray space communication. The infiltration stage, which is sort of gray to blue space, and then the moving laterally stage of the attack. And so for cyber people, this is actually very useful to have because they're not used to thinking about this problem in this way. And so this is just some additional fun educational materials we've put together. So this is a really hard problem, particularly from the science side. There's a very famous report put together by the JSONs in 2010 talking about the science of cybersecurity. And they really emphasize the need to get reproducible observations of computing systems in order to do science. So that is the essence of science, right? Is really reproducible observations. And in other domains, whether it be land, sea, undersea, air, or space, this has been the backbone of how you protect domains. You really need detailed observational science models of the environment to understand what is normal. Um, this means you really have to take an observational science approach, which requires generating what we call significant AI-ready data. In this space, people have enormous quantities of what we just call logs, but they have very, very little AI-ready data. And so our work has really been focused on addressing those effects, those issues, really creating, mechanisms for creating an enormous anonymized internet traffic data. And we have the largest sort of publicly available data sets in the world, over 100 trillion observations, which allows us to really do this scientifically hard problem, which is very exciting. As I mentioned before, privacy, whenever you're dealing with the internet, is just extraordinarily important. And one of the unique things about this work, which is really a hallmark of Professor Pentland's work, is sort of really looking at all the parts of a problem. Okay, you need big data and there's privacy issues. Well, let's talk to lawyers. Let's figure out what it really takes. And so one of the things you discover is that if you want data, you talk to network operators, they do have the right to collect and analyze and share data, but only if it will improve the network or its operations and security. So that means that anybody who gets that data has to inherit that intent. Now, fortunately, there's a group called CADA at the San Diego Supercomputing Center that's been pioneering this work for many, many years, and we've been able to leverage their work quite significantly. They've developed legal frameworks for doing this, and we've just sort of copied that. MIT also has similar frameworks, and the main thing is coupling the anonymization scheme with the appropriate legal agreements to do what we call trusted data sharing. So you get data from others, they control the anonymization, and you and your institution agree only to use the data in very prescribed ways. Obviously, you're not going to de-anonymize the data, and you can only do certain things that are inherent with whatever the intent was of the people who got the data. So that just cannot be emphasized enough. But if you do this, people are actually quite willing to share data, which is wonderful. So another thing that we do that's pretty unique, and so now we'll get a little bit of a lesson of how the internet actually works. So all these packets I mentioned, they are all, they're like an envelope in the mail, right? They have two pieces. So the outside of the envelope, which has the information about where it's coming and where it's going and the stamp, etc., and the payload here, which is the inside. And there's this thing called the IP address, Internet Protocol Address, which is kind of like the zip codes, right? So you have a zip code of where it came from and a zip code of where it's going. So we ignore all of everything but these zip codes, right? So this actually helps a lot with this privacy thing. These zip codes are kind of the least protected, or there's no presumption of privacy with respect to the zip codes of these things. And we ignore the entire payload. All payloads should be encrypted these days, so there really shouldn't be anything you can do with them anyway. But we just strip out this little bit here. So we take a little bit of everything, which is kind of unique in this work. So when we collect the data, we get a bucket of we call NV valid packets, where we just have these zip codes, these source IPs and destination IPs. We then anonymize them using a method called CryptoPan, which has been used in this space for many, many years. So we anonymize all the source and destination IPs, and then we create a hypersparse matrix using the GraphBLAS. And the GraphBLAS has been the real game changer in this technology. Nothing I'm going to talk about today would have been possible without that technology. And then we create these hypersparse traffic matrix files. So what are we really doing here, right? So we have a network. These are the zip codes or IP addresses. This is our network here. And then we anonymize it, which essentially means we're reordering all the rows and columns. The anonymization key is held by whoever owns the data originally, so we don't have it. And then we're going to do everything on these anonymized traffic matrices. And we have also assigned agreements that saying we're not going to de-anonymize. And obviously, legitimate institutions are very, very concerned to make sure that people don't violate those agreements. So this is a very good mechanism. This is a routine way that data is shared in industry all the time. And so this works very, very well. And it's conformant with things like GDPR and other global regulatory schemes that cover this kind of work. So then we can do all kinds of fun math on that. So here's a stream of data. So this is just, you have data flowing over a network that you can break up into these matrices. And there's a whole bunch of quantities you can compute on them. You can compute these on any graph, any streaming graph. I won't go into the details, but there's about 9 quantities here you can compute very easily. The math of these is shown on the right. Both in summation notation and matrix notation. You basically create a matrix covering a time window t, and then there's just a bunch of very simple calculations you can do that give you all kinds of interesting statistics that you can analyze here. And again, the GraphBLAS makes this very, very efficient to do, and there's wonderful binding to the GraphBLAS in many, many languages, so it makes it very easy for this work to proceed. Some of the performance breakthroughs that make this happen. So generally, when we do this on data, we get enormous compression. We can get about 1 bit per packet. A typical packet has about 10,000 bits. So by definition, our traffic matrices are going to be 1/10,000th of the data. So this is very easy to ship around. This makes it very easy to do this work. We've also demonstrated using the GraphBLAS, on a supercomputer that we can analyze enormous quantities of data. So we can analyze, with 1,000 servers, 10x times the American internet traffic in real time, which is, really makes this work possible. So if I have 100 trillion packets to analyze, I can do this using with available resources. So the GraphBLAS is great both for the enormous compression and the fact that it's a mathematical library that does the math on these traffic matrices very, very fast. So what do we do here? So, we're doing AI, but perhaps a little bit different than what you've normally seen. So we basically take our traffic matrix. It's a giant sparse image. It's a quadrillion pixel image. So these are, in a certain sense, the largest of larger AI models. We have a sequence of these matrices. Those can be viewed as an image or a movie. We know how to do AI on that. We're essentially doing graph neural networks. We're basically taking this image. We're doing some computing some of these quantities, and then we use these to fit various models. And so one of the big differences here is that instead of mostly AI is used to categorize data, but in the network protection domain, the adversary signatures change so rapidly that doesn't really work too well. So what we do is use this data to create very high precision background models of what is normal, really that core observational science question. And then once we know what is normal, we have this model here that we can then use to look for deviations. So I can say to you today that we've actually have a good holistic model of the internet background. So if you put down a sensor and you collect a certain number of packets and you see a source emitting a certain number of packets at a particular time, I can tell you what the probability is of seeing that source at a different location at a different time with this relatively low dimensional model here, right, which has about 5 parameters. These 5 parameters are location specific. So this is very consistent with sensing and other domains. You have a low dimensional model that you can fit. It does depend on the location, but then you fit these parameters to that location, and these don't change very, very much. And so we have this great background model here. We can do very interesting science with this. I'm going to just talk briefly about this one part of this, which is just the intercorrelation time. So what's the probability if you see a source, seeing it again at a later time? It follows this sort of everything in here, by the way, are heavy tail distributions. So heavy tail statistics dominate the internet. So, if you're interested in heavy tail statistics, which I think people should be, there's no better data set to look at. So one of the things we can look at is we can look at, how do we differentiate benign and malicious traffic? Looking at some of the mathematics, it's somewhat akin to an orbit. You can imagine benign traffic is kind of like high-flying satellites that are orbiting your location. They're easy to spot. They don't move very much. They drift very slowly versus, say, adversary traffic, which is like a low-flying rocket, which if you look up and you see it at all, you'll see it very briefly and you never see it again. And we see there's, huge gaps between the trajectories of benign traffic versus malicious traffic. This just tells you that malicious traffic is trying to hide, so that becomes its signature, which it makes it very easy to detect. So there's just one example of how we can apply these kind of ideas to actually detect things. We've created this Cipher Censure. We've deployed it. It's won many awards. And it's actually now part of a thing called the IEEE MIT Amazon Graph Challenge. So the code, the specification code and data are all available. We have a number of companies that have been early adopters. NVIDIA has been a big supporter of this work. We're very grateful to that. And so these capabilities are available, and we're working with many companies to get these capabilities out there. I will skip over some of this. It's had enormous impact. And I will then just leave. If you want to hear more about work like this, we have our conference, IEEE HPEC 100% virtual conference, which will be in September, and much more of this work will be covered there. So we encourage people to that. So that hopefully gets people interested in hypersparse matrices and how they're useful. And I assume I have used all of my time, and I'm happy to take any questions if there are any. Thank you very much.
Thank you very much, Jeremy. I actually, what I'd like to do is maybe take quick clarifying questions now as necessary. But I'm thinking that if the speakers each take 25 minutes and we just run the talks back to back, we'll end up with about 15 minutes at the end of the session, during which the 4 of us could do just a little bit of a panel session of discussion, which I think might be interesting to us and interesting to our audience. So are there any quick questions for Jeremy? Okay, I have one, but I'll hold it until the panel discussion at the end, and I'll turn it over to Tim Davis, who will talk about the SuiteSparse implementation of the GraphBLAS. Full screen. Jeremy, I think you're still sharing.
No, he's.
Oh, no? Okay,
Yeah,
okay, we're good. We're good.
All right. Well, welcome everybody. This GraphBLAS project that Jeremy mentioned for this anonymized traffic analysis has been quite a lot of fun. Jeremy asked if I've been watching this API for quite a while. This is this design of a library to implement the vision of being able to take a graph algorithm and write it as a collection of matrix primitives like Legos. And the idea behind the GraphBLAS then is somebody could write these little Legos, somebody, who would that be, and make them fast, make them parallel, And then the person building the Lego race car doesn't need to care how fast, how the Legos were made. They just want a fast race car and run it down, say, a Pinewood Derby track. Now, it won't beat that finely tuned. It often won't beat that finely tuned, crafted Pinewood Derby car that you race down the track, but you'll build it in 20 minutes as opposed to taking 3 months. And if you've got an algorithm you want to analyze, you can put together an algorithm really quickly with this API, clicking Legos together, and get pretty decent performance. And in fact, sometimes it can beat the Pinewood Derby, this crafted Pinewood Derby car in terms of performance, not just expressibility, but also performance. That's a double win. We see it, as Jeremy mentions, what the GraphBLAS is trying to do is raise the floor on performance, that anybody can write a parallel graph algorithm. It's not just for the expert domain experts to write. So this is the idea of GraphBLAS, graph algorithms in the language of linear algebra. And we're trying to push the boundary on, we've got all these algorithms we like to write and the API underneath it. And as we create new algorithms, new graph algorithms, we realize, oh, hey, we need something else in the GraphBLAS, another matrix operator to do this. And so there's a back and forth between those two. So there's the LA project that has all these algorithms, GraphBLAS that then is the toolbox. So in the toolbox, the fundamental idea is the notion of a semi-ring. Now, for the pure mathematician out there, we're not doing pure semi-rings. We're doing maybe a pseudo semi-ring. We might want to call it something different because there's some properties of the semi-ring that we don't need. We need to actually drop. So we have some of the features of a pseudo ring, not semi-ring, not everything. What a semi-ring does, it just simply redefines what it means to multiply two matrices together. And in the conventional semi-ring, we've got the plus times, where you say you're doing the put your finger down and do the dot product version of matrix multiply. You're summing up to get the one term in the output. You're summing up. You're multiplying pairs of numbers, and then you're summing them up. Well, there's two basic operations going on there. There's the multiplying. That's the AIK times BKJ. You're multiplying those pairs of numbers. You're taking all those multiplication results and summing them up with another operator, which is plus. So this is the plus times semi-ring, and the domain is, say, the real numbers. Okay. And this sigma would work nicely if the matrix was dense. Every pair of entry is there. Well, now in the sparse case, we've got matrices that are empty. If you've got a matrix that's 4 billion by 4 billion, you can't put every entry in every position of that matrix. So what we do then is, instead of summing up across everything, and we use different algorithms, we always use dot products, but this is easy to describe. You work across these set intersections. So matrix multiply is intrinsically computing set intersections, which is really useful for a graph algorithm. And we don't have to stick then with plus times as well. We can rip out the plus and put in something else, like put in a min, and rip out the times and we've got a spare plus. Put the plus in. You get something called a min plus semi-ring, and that's really powerful. The min plus semi-ring is really useful for shortest path problems. If you take the weight matrix and just raise it to the nth power in the min plus semi-ring, you get all pairs shortest path, just like that. The plus operator has what's called an identity value. With a plus, it's 0 because it's the thing that does nothing. X plus 0 just gives you X. The monoid identifier for min is infinity. So if you take the min of 3 and infinity, you get 3. Now, I guess technically that would not be the real numbers because infinity is not a real number, but right, where we handle these little idiosyncrasies and bend the pure math a little bit. Min plus is a pure semi-ring though. So the true semi-ring has these two things. It has two monoids. We just use one. It has the plus thingy, the additive monoid. It has to satisfy all these properties. And we keep all those of the semi-ring. It has to have an identity value. We call it 0. They ought to be in the same data type, domain. That's a commutative. It's associative. The next thing, the multiply monoid, we drop all of that and we just say it's an operator. It could be divide if you like. And it can be pretty crazy, as I'll show you in some of the examples. Here's an example of it's like the first graph algorithm. And what's my time? Okay. It's like the first graph algorithm is breadth first search. Yes, we can do a breadth first search pretty fast. On the left is the traditional sequential method. You've got a queue, you stick nodes in, you see it, pull it out, and you say, oh, who can I see? And you put them in and you keep going. If you write code like this, it's sort of like writing triply nested loops of a matrix multiply. You don't do that. Like if you're writing in MATLAB or Julia or something like that, so you don't write matrix multiply that way. You just write star. So let's try to use that vision for graph algorithms, and you can do that. In fact, the matrix, you can do the following. If you have a vector, this is this vector Q here, which is the green vector with the 2 4s in it right here on the right. I'm not sure if you can see my mouse on the screen. That's the current frontier is nodes 1 and 3. That's where you're at level 2 in the BFS. And now we want to find level 3, which is nodes 2 and 6, not node 4, but nodes 2 and 6. If you take that frontier, take those nodes and multiply it by the matrix, what you're doing is you're in parallel looking outward as a single Lego, single matrix vector multiply is looking outward from those frontier nodes, from those nodes in the frontier to the nodes they can reach. Now they can reach somewhere back up in the tree where someone's been seen before. That's node 4. We don't want to see that. So what do we need to do there? And we don't want to just matrix multiply these two numbers in the conventional summary ring either. But first, let's talk about what do we want to get out of this? We want to get just 2 and 6. 4, you've been seen, go away. And that's called the mask. And there we say, if you do not have a parent, you get to have a parent, you get to be seen. 4 has a parent itself. It's the root of the BFS. So you've been seen, node 4, so go away, we don't want you. So it's just 2 and 6 is the result of this matrix vector multiply. In positions, I should say, 2 and 6. So the 4 would be crossed out. Now the values of the output vector here in red, I want to also compute the breadth first search tree. And that is done with the summer ring. I want to say that the parent of, I want to record who found node 2. Now, who found node 2 is either 1 or 3. Okay, and so imagine you're doing this matrix multiply. What you want out of the multiplicative operator is you want AIK, which is the edge, times QK, which is the finding node, which is K itself, node K. I want the multiply operator, the result of AIK times Q of K, I want the result of that multiply to be K itself. So I'm not using values from the matrix. It's a positional. It's called an indexed operator. It's an operator that depends on the position of the entry in the matrix. The answer of the multiply is K. Then I want to say, maybe and see node 2 would be the position where it'd say, oh, I see both 1 and 3 as my multiplies, and I want to add them to get 4. I wasn't seen by 4. I was seen either by 1 or by 3. So pick one. Pick the min, that would be 1. Pick the 3, that would be max. Or let's come up with a creative monoid. I don't care. Just give me one. I don't care. Pick one, anyone, Tim. Just do it. Do it quickly. This is I call the any operator, and it gives me the freedom to put in a benign race condition to do this faster in parallel. The any of x and y is x, or it's y, or sometimes it's x and sometimes it's y. It's whatever I want to give you. Now, I won't give you, if you do any of 2 and 3, I won't give you 1. I'll give you 2 or 3, or in this case, 1 or 3. I'll give you 1 or I'll give you 3. I won't give you 4 or 7. If you don't like it, use the min. And what that allows me is freedom to loosen the parallel synchronization and give you a faster matrix vector multiply. So basically this pseudocode, you can almost write this just this way in MATLAB, and it's 2 lines of code inside the loop to do the breadth first search. Now, so how fast is it? Well, whoops, oh, there we go. I'll show you in the next few slides. These are some of the kinds of matrix operators we can do across these different operators and summary rings. And we provide these basic operations on our sparse matrices that I represent internally that are then representing graphs or some other, it could be actually a computational science problem with matrices. Entries have any data type, including ones you get to make up on your own, on the fly, that the library has not seen before. And I'll compile you a kernel on the fly, not me, but my code will, with a just-in-time compiler, with those operators and data types. We can multiply across any subring, any pseudo subring. We can do non-blocking mode, lazy evaluation. There's that mask I explained. A mask is basically this matrix assignment where C of mask equals A is like a loop across all ij. We don't do this. It's not n squared time. If M says it's yes, you can go, then A goes into C. If Mij says no, then Aij cannot be assigned into Cij. So it's like a bulk if statement, and it's one of the Legos in these algorithms. What algorithms do we have that we can build on top of GraphBLAS? Dozens of algorithms. Some of them are quite stable. Some of them are in various stages of progress that the release. This is all these codes are available, and they're even the experimental codes are being used in production. Just the API might not be stable, and you've got to think about maybe some performance issues here and there, but they're workable. They're pretty good. Max independent set, triangle of centrality, K-core, triangle pulling, Fiedler vector, matching, argmin, argmax. There's a funny summering for you, where like the indexed operators, it needs to know not just what the min value is, but where did it come from? So the multiplicative operator needs to provide that information. So the operation in the multiply needs to know the index of the operator, of the value in the matrix. We just recently came, I had some students work with me that recently did some 4 undergraduates, max flow, edge this past year, edge between the centrality, rich coefficient, coloring, and I'm sorry, also, sorry, I left one out, swapping edges to get a random graph randomization. Jeremy talked about graph randomization. We can do that with randomize all the connectivity, not just the IP numbers, say, all the connectivity where every node has the same degree. Well, some of the performance rules are really, really exciting. In particular, this max flow push relabel. It's beautiful. It's all beautiful MATLAB, just a ton of operators and just line after line of Legos, linear algebra after linear algebra. There's one for loop in the entire code. It's a while we're not done, keep looking. Max flow, you've got a source and destination. You're pushing flow from the source to the destination. This is a parallel push relabel code because not in his code, not in my student's code. There's no single parallel pragma or parallel thing in his code at all. Just each piece of the Legos, if you will, the GraphBLAS calls are parallel. So it was a simple algorithm. Well, it was challenging, I should say, but he could do it. He's a senior honors student who could do it in his course of his honors project. This didn't take a PhD, and yet if we compare it with a very high performance parallel graph algorithms library from UT Austin, Galois, it's 2 to 6 times faster than that. So we can get some decent, really really great performance. We benchmarked ourselves again. This is the Twitter matrix. It's got 60 million rows and columns. It's on 1.5 billion non-zeros. And I compared it with the same syntax. So I've got a MATLAB API which overloads all these operators. And you can do this very syntax in MATLAB, but underneath the hood, it's a GraphBLAS matrix, not a MATLAB matrix. Same syntax. And MATLAB takes 23 seconds, and I take 2.4. And I'm almost 10 times faster, and so forth. So this column here is the speed up of these typical matrix operators. There's other operators that MATLAB can do, and this is one line of MATLAB, Cij equals A. I can do Cij equals A 1,000 times faster than MATLAB can do the one statement, C paren I, comma, J, which is an assignment, a matrix subassignment where all the matrices are sparse. Now, MATLAB has this notion here of, it's called logical indexing. And it's exactly the same thing as the GraphBLAS mask, except that the MATLAB logical indexing, even though it works exactly the same as the GraphBLAS mask, it's literally 500,000 times slower, like 7 seconds versus 2 weeks. Like I let my laptop sit in a room for 2 weeks in MATLAB, finally finished and computed the masked assignment. And I ran it in GraphBLAS and it took in MATLAB with the same syntax. It took 7 seconds. So it's I call that there's a theoretical term for that. It's called crazy fast. No, it's asymptotically faster. It's n squared versus n log n. That's what all it is. Okay. So when n is big, n squared is way bigger than n log n. That's what's happening under the hood. So it's crazy fast. I've also compared this with the Intel MKL Sparse library, and it's typically faster. MKL has this place the first time they analyze really carefully so that the next time can be faster. Well, I beat their second time with my first time, usually. Well, I've got one exception right here. I'm twice as slow. So they're pretty good. They're hard to beat. Good piece of code, but we're working. So we've got some nice kernels under the hood to build these graph algorithms on top of. Now you can also write graph algorithms in, say, Python. It's also very expressive, which is great, but doing this kind of thing in Python with just pure Python can be incredibly slow, but it's expressive. So NetworkX is, I don't want to downplay the importance of this NetworkX Python package. It's got hundreds and hundreds of algorithms. We've got maybe 30, okay, in LaGraph. So we've got a long way to go that direction. But GraphBLAS brings these numbers in the table here. These are matrices on the top, or graphs on the top, and different problems on the left here. The numbers you see are not numbers of seconds. No, it's how many times faster GraphBLAS is, like 250 times, or 2,000 times, or didn't finish, or 21,000 times, days and weeks versus seconds. And it's even faster than SciPy, which is a package built for high-performance sparse matrix computing. So we've got some good good performance here compared with the GAP benchmark. And Scott Beamer wrote this, the GAP library. It's a very high performance. It's not really a graph library. It's a collection of just six parallel graph algorithms. It's not a general purpose tool. It's not meant for that. It's meant for benchmarking. What is the fastest pure parallel C++ breadth first search we can write? And on a Twitter graph, that's 0.22 seconds. And a GraphBLAS that's much easier to write. You don't have to do parallel pragmas, atomics, and all kinds of crazy stuff. It's 0.35 seconds. Okay, so I'm not quite as fast, but I beat the gap with betweenness centrality, which is a different metric that says who's important in the graph. It's a more complicated algorithm, and my code is actually faster. Now that's, if you think about it, that's not really possible to be faster, because in a sort of a theoretical sense, you could take GraphBLAS, it's just C, parallel C under the hood. You could strip away all the beauty, strip away all the Legos, just smash together those kernels, fuse together the operations as you can, and you end up with something like the GAP code by Scott Beamer. You know, you just, and then that code should beat. You should get a speed up to do that. Well, it's slower. Why? The reason that I think that the betweenness centrality and the gap is slower is two reasons. Is the Lego style of computing gives us much more freedom to explore the algorithms. And we were to see different places to go with the algorithms that are better. And like doing bulk source multiplying, I mean, not just matrix vector, but matrix, looking lots of source nodes at a time. And then Scott Beamer, for the BFS, invented something called the push-pull optimization of breadth first search. He didn't, something like a breadth first search happens in betweenness centrality, but Scott didn't write it. Why? Because, well, probably because the code is already complicated enough. Well, push-pull optimization in betweenness centrality, or the BFS, is do you multiply A times X or A transpose times X? X times A, like AB is B transpose A transpose. Take your pick. That's push-pull optimization in a matrix. So it's very simple to implement, and we actually beat the gap. Now, these other codes where we can be 3 to 5 times slower, but you can write the codes much faster than the gap, something like the parallel C++. So the impact of GraphBLAS, it's built into MATLAB already. When the MathWorks saw this, they said, oh, we want some of this. So GraphBLAS is now inside MATLAB. So if I go back to my other slide here, I have to kind of clarify. Let's see, where is, yeah, I didn't mention this. C equals A times B, where A and B are sparse. I get 1x speed up over MATLAB. Exactly, because I am. MATLAB is GraphBLAS at that point. It's benchmarking against itself. But I got a substantial speed up over the older single-threaded sparse times sparse in MATLAB, which I had written for the MathWorks about 15 years ago, which I beat myself by a factor of 8 on my 8-core machine, something like that. The GraphBLAS sits inside as the engine in a package called FalkerDB. It's a high-performance graph database. 80% of all prescriptions, just one example, filled in Israel are analyzed with FalkerDB and GraphBLAS to look for hazardous drug interactions. It's also a RAG, which is a retrieval augmented generation mechanism, which is a way of getting an AI language model to stop hallucinating a little less, at least. You need to query a graph database. It's in many other places. Jeremy mentioned, and my slide is out of date. I mentioned 40 trillion packets. He's now to over 100 million. The Air Force is getting 100,000x speed up in finding nasty network traffic. So they're very excited. And you can even assemble a finite element matrix if you're into finite element methods. One matrix multiply with a clever summering gives you a finite element matrix from the pieces. At least so far the pattern, not yet the values. We're working on that. Got a lot of people involved in this. There's a steering committee. There's a working group for LAGraph, C++ API committee for the GraphBLAS itself. There's a Julia interface. There's me at the bottom of the heap here. I'm slugging away at the code, and with some of my students, and Python. This needs to be updated here. There's a Go interface and Go implementation by Pascal. And tons of contributors to LAGraph itself. And the reason why there's so many contributors to LAGraph itself is it's so open and so easy. Well, it's a challenge already. It's still a challenge. What becomes hard for a graph algorithm expressed on GraphBLAS, the code is now dead simple. The code is just think of what do you need to do to write a piece of software. There's an algorithm you need to come up with, the math behind it, and then the code. When you're coding in C, C++, sometimes the code can be very intricate. And yeah, the algorithm dead simple and the math is simple but now you got nasty data structures and the code gets really complicated and you get memory leaks and blah, blah, blah. That's a challenge. GraphBLAS, you don't have issues with the code being complicated. Usually the code is very, very simple. It's just clicking the Legos together. The hard part is knowing which Legos do you pick? What math do you pick to express your graph algorithm? That's the challenge. I mean, my undergrad students might spend a whole semester or a whole year learning GraphBLAS and then writing 100 lines, 200 lines, 400 lines of C. It's like, you did that for your whole senior project. That's boring. Well, yeah, because the code is simple and sweet. It's the math that's hard. And that's where things ought to be. Expressing the ideas and the algorithms and the math should be hard. So let's see. I've got a few more minutes, correct?
Well, we're trying to.
Oh, we're shifting. You want me to end right now, don't you?
Yeah.
Okay, or pretty
take
close.
Another minute.
Well, this is it. This is it. My last slide, Ben. Yes, I forgot we're 5 minutes. I was looking at 6:55. Sorry. So it's an expressive mathematical language of submarines. These bulky kernels or the Legos. There's lots of work to do. I get to make an opaque data structure that's easy for users, and then it's easy for me to say, oh, I can do matrices like the hypersparse idea of storing, which was actually Hayden's, and you and Hayden, yeah, John and Hayden. I can implement it inside these Legos, and nobody knows the difference from the outside. Just the performance is suddenly different. Excellent performance can rival, even beat sometimes highly tuned algorithms written in C, C++. You can create your own data types, your own submarines, your own operators, and I'll compile them at runtime. Like you don't have to recompile my library. I see the strings that define those operators. I write a file with the code within your kernel, and I go compile and I open it up and there it is. And you come back next week or tomorrow and I've saved it in your home folder, pull it in and there it is. So there's no penalty for being creative with these submarines. lots of future ideas, kernel fusion, CUDA, and more graph algorithms. So with that, I will pause and take any questions.
Okay, thank you, Tim. So again, any short clarifying questions for Tim? And we're going to try to run 25 minutes for a talk here and leave about 10 minutes, maybe 15 minutes at the very end of the session for a general discussion between us. So any questions for Tim at this point? Okay, hearing none, our next talk comes from the sparse matrix computation world rather than the graph computation world. But as we've been talking about, those are really the same worlds in some sense. Piotr Luszczek is going to talk to us about Sparseblas, which is, well, he'll tell us what it is, the new interface to sparse linear algebra operations. And Piotr, let's, if you could finish about 7:20 or so, maybe that'll give us a little bit of time at the end for discussion. Thanks a lot. Take it away.
Okay, with the 7:20 in my mind and trying to keep in time, let me proceed. So thank you, John, for an introduction. And let me just say on my side, I guess it's something completely different, yet something almost the same as how I would open up my part of the session today. So Sparseblas is the new interface, but we'll see that it also builds on the old one, and it's also in the language of linear algebra, but it's basically just a small sliver of it. So let's proceed. So here is the quick outline. So I started with my name, but really it is there's a lot of people that are behind it, and not all of these people that I'm listing here are active at every single moment that we started this about 2 years ago, but they are participating at least once or twice a quarter. And so a lot of institutions as well, and especially vendors, and vendors will be important to this effort, because it's something a project trying to unify a vendor interfaces to Sparseblas. So why do we talk about Sparseblas? What we really want to do is we want to transition from dense linear algebra, dense matrices, and dense vectors, where all the entries are stored explicitly, regardless of their value, and we want to just go into a space where only some entries in the matrices are stored and represented in memory. And so that's the important part of it, is that like in the previous talks, we only want to store things that matter algorithmically, that matter semantically, and most of the other things are in a sense gray areas, and we should represent them in this particular case by floating point zeros, which we omit. And so in dense land, everything is very simple. So all entries are stored explicitly. There's a very well known format for rows and columns that are just all there. They're all always sorted from left to right, from 0 to n-1. If you're a C person, from 1 to n. If you're Fortran or MATLAB, there are vectors and matrices are conceptually the same. It's just a different number of columns, different number of rows, but the storage is identical. And going to sparse land, I mean, things all of a sudden change very quickly. We need to now count how many zeros and non-zeros we have, especially. And there've been different formats over the years. You probably have heard of a coordinate format, sparse row format, the different ELL. So these are special formats that create small letter blocks, diagonal formats. The other issue is that the elements are not always sorted. So I could I could basically accept the elements from some other piece of my code that is just not behaving in a sorted manner. And all of a sudden vectors can become sparse too and have different formats from matrices, because there is only one say one row and one column. And most importantly, which complicates things the most, now we have multi-step algorithm. So again, it's very similar to what we're talking about GraphBLAS before, but here basically those individual steps are different optimization phases, if you will, symbolic phase, memory allocation phase, numeric phase. So we'll go into the details of that. So this is just a taste of things. And for the dense BLAS, they started as a Fortran interface that later was extended to C, and things were easy because again there was not many options in the dense land, but in the sparse land where there are just so many different options, and at every step of the way that getting some help from the compiler from the language is important. So this is why we're very much looking at C++ that simplifies this combinatorially huge space of different options that we have to put together. So I'm kind of teasing it that the writing this in C, all the options right away is impossible, but I'll talk about a little bit more how we can actually tackle that. And finally, because we're not really focusing on these very interesting algebras that Tim was talking about. Here we are specifically in a floating point area, and no other formats are really important. So what is important is the handling of nonce and infinities. So over the years, with different group of people, we were trying to define the numerics and behavior of nonce and infinities, things, these special values in the IEEE format, and have that handled correctly at the API level. In the sparse land, we have a problem because those zeros basically are not really stored. So do we really multiply a 0 by a none, which in dense land always generates a none, or do we do something else? So defining the semantics of this kind of operations is what we concern ourselves with. So with all these problems and all these issues and different options, let me just talk about the scope. So historically speaking, the scope was quite narrow. These are some past efforts that try to work out the sparse matrix standards. Unfortunately, there were multiple ones over the years. They were designed back when the GPU was either non-existent or was not as important as they are today. AI and machine learning folks did not have their needs addressed because they were basically doing things not in a as prominent fashion as they do now, and C++ was not really updated as often and worked out as well as it is today. So with all these things at the bottom, those older standards for sparse floating point BLAS were really kind of lingering in the background. So with the vendors that actually provide some of these things, we just got together and tried to unify this. So this is just a taster and kind of saying that the vendors already do this functionality. However, if you look at the slide, this is Intel, and then the middle is Hypersparse from AMD, and the bottom is NVIDIA. No particular order. The point is that there's a lot of similarity between the interfaces, and yet there are many differences. So if you want to just multiply a matrix times a vector, and then you want to change the hardware and give your code to your friend that has a yet another different piece of hardware, you have to keep changing code, and we're trying to avoid that, and basically have access to these vendor optimizations through a single single interface. And so what goes in it? So I already mentioned the a few things. So we're trying to unify the conventions. We're trying to look at numerical linear algebra libraries that do these floating point operations, the vendor ones and the ones coming from the community, and have things unified to the point where we can just exchange them and plug and play between them without changing code and introducing bugs. And yes, I mean, cross vendor, current vendor or future vendor, we want to be able for the vendors to come in with their hardware and just immediately be compatible with a lot of software written for a common standard. So I mentioned the team, and so how does the team interact? So we have these different events. We try to organize a birds of feather at ISC. We had one at ISC just ending in June. We will have one at the supercomputing coming in November in St. Louis. The vendors are there. And so, but there are also other people, numerical analysts, and enthusiasts, people coming from applications, finite element, and all that. They bring their needs to the table and are heard. And eventually, after these 3 meetings, 2 in 23 and 1 in 24, all 3 of them took place in the foothills of the Smoky Mountains in Knoxville, Tennessee, and we had we have a document that we right now evolving into a working standard. So this is the number of on the archive preprint. Feel free to read it. So what's in the effort right now? So we have a GitHub organization. So this is the main link. Sparseblas spelled with the appropriate capitalization, and we have some subrepos in there. The reference. So we already have a C++ reference implementation that is still work in progress. It is evolving as we're changing and adjusting the different bits. And that implementation calls in to those vendor libraries. So basically, when you come in through that working reference implementation, you basically already have some notion of uniformity between the vendors. And there are what we call mini apps, basically things that are more complicated, the layer on top of it. And so we're working at randomized linear algebra and then Krylov solvers to go on top of it. And there's a Google group where we email things each other, have some lightweight discussions, and coordinate for the events. Anybody is free to join. This is really and it's not a secret society. So just drop me an email or anybody else that you saw on the list, and we'll be happy to add you to it. So which data formats we support? So we're trying to make this a usable standard, but at the same time, we also want to make it a manageable standard.
I'm just going to interrupt, Peter. Yes. Your slides are looking cut off to me at the top. I don't know if others are seeing this.
Yeah, we're seeing it too.
Yeah, we're seeing it too.
I thought
it may be the wrong size.
Well, you're in the scrolling in the window of your slides, and we're just getting the top, like you're.
And it's flashing too.
Yeah, you're not in like slide mode. I know these are PDFs.
Yeah, that's a PDF. I'm just sharing a basic
Maybe stop
window.
and reshare.
Yeah, stop and reshare.
Yeah. Because it was okay at the beginning. It just changed at some point.
Mm-hmm.
Perfect.
Yeah, that's better. There
That
you
looks
go.
good. Thanks, Pete.
Yep. Okay, so going through the formats, we want to initially, at least for the version 1.0, which we still don't have, we want to have the common formats, but not all the formats. So this is things that we're intending to include. We're looking at this new MD span that was accepted in C++ 20. So that's accepted officially 5 years ago. but we'll talked about probably for a decade. So it's uniformly implemented, and it's a very useful vehicle for storing various things in the standard. And the things that we're planning to exclude, those more advanced standards. So these would be optional extensions. But because they are already supported across many vendors, there will definitely be those included in the inference implementation, and it'll be really easily accessible and planned for the next version. So what are the operations? So this is kind of the rundown of different ones. You can see it just overflows the slide. So there is kind of it's a summary that is like put together to be as compact as possible. Really, you should refer to that archive document where all of those operations are listed in more detail. But generally speaking, we have some utility operations, norms, transposes. Sparse matrix operations are between a sparse matrix and a vector, and a sparse matrix and another sparse matrix. And so these are the workhorses. But there are some other things that basically do some basic selection. And there is the sampled matrix multiply. That's basically the AI and machine learning folks like this kind of things using usually a lower precision format. So we're going to be talking about those things as well in just a second. So moving to multi-stage operations. So it turns out that in a complicated setting, when we have a one GPU or even multiple ones, we have different memory spaces between them, and we have the sparsity pattern of the matrix being in a different formats, and we want to compute things. It turns out that it is useful to do it in multiple stages. So we usually call them symbolic compute, symbolic fill, and an actual numerical stage. So we first try to find out how much space we're going to need, so that there would be the symbolic compute, and that allows pass on things to the user that wants to, for example, do some custom allocation. Then there is a symbolic part when we actually fill in the structure and put it in the allocated space. And finally, we compute the values. So these are the multi-stage interfaces, and they use these internal structures that depend on the format, the data type, and other things. And so most of those things are internal, but some of them are also done explicitly. So we'll talk about the difference between the view and the ownership of the data. So how do the vendors fit in? So again, there are already in the reference implementation, we're trying to be compatible with the major vendors. They already have this in libraries, so they already have these multi-stage operations. So this is a common thing. Some of those are present, some of those are not. So it is possible that some of those steps could be doing nothing, because the work was done in the in another step. And a good example to look at is available on GitHub, and that's from the CUDA library samples repository in the NVIDIA organization on GitHub. And so this is an example of a sparse matrix multiply that they have in there that kind of shows you step by step how these things can the stages occur one after another. And of course, depending on the application scenario, some of those stages you can actually reuse, and others you'd have to repeat and recompute because something changed in your matrix. So what are structural and numerical considerations that they were looking at? I mentioned at the beginning, we were all about floating point numbers, and the special value is a 0, and we try not to store it. But for some formats and for performance reasons, sometimes they are they could be useful. So there are these block sparse.
Piotr, sorry to break in, but your
Yep.
slides just went weird again. Could you
Yes.
share again, please?
Yeah, apparently, yes.
I don't know what's going on.
Yeah, I don't never
Single
happened
page
before.
view.
Yep.
Yeah, thank you.
because you got to
Yep,
scroll.
thank you. Please let me know when it happens again. That's very annoying. I don't quite understand why it's happening. Okay. So so block formats, we're not planning to support them right now, but the vendors definitely do. So there's an easy way to plug those in, and probably the next version of the standards will be included. Those block formats, of course, are done for padding things up, aligning things a little bit better, because the hardware most of the time is catered towards dense storage and dense formats. So we're working on these sparse floating point matrices, but we're pretending that they have a lot of regularity, and that's mostly for cache line and coherency issues, and coalesced memory transactions on GPUs that maximize the bandwidth. And so so we have to basically start differentiating those zeros. Some of those zeros are there because they were there from the beginning when the user handles the matrix. Then we might introduce some zeros to make the matrix look regular, and maybe do it for some other reason. So that kind of creates a notion of multiple zeros. We really don't have time into getting into that. We get into the details of this basically when discussing semantics of these operations, of how they deal with different zeros during conversions and computations. So these things are the most important when we deal with special values such as nonce, because again, taking a non number, a very normal value for IEEE arithmetic that was basically introduced to represent a result of certain illegal operations. They are so multiplying none by a zero creates a none, and basically it might, for some people, do not want to see them in their operation. So we have to be very careful how to propagate them, and how to turn them into into values or make them disappear depending on the user wishes. So we have a numerical analysts and people that basically just chase these issues through many different other libraries and interfaces, and help us square this out. So again, some zeros that they have to be there because they were given by the users, or we were told not to eliminate them. There are some implicit zeros that we basically don't store, and there are padding zeros. And so we want to make sure that only those explicit zeros that should be there should propagate the nonce. So this is generically speaking our current stand on that. And moving right along, so IEEE in 2019, and really 2020, when the new standard was ratified, added new computational type, 16-bit. Before it was only storage type, and so the intention is to support them because it's quite ubiquitous now on most of the hardware. And another thing that is ubiquitous is this thing from AI and machine learning folks, the brain float from Google. It's trying to be both small and at the same time really big, because it has the really large exponent borrowed from the single precision format, sacrificing a little bit on mantissa and its accuracy. So so yes, those are the most common formats. But again, we try not to bloat the initial standard. So more more precisions planned in the future. There's the issue of mixing precisions. So not all of them will be supported right away, because it's, again, we have this combinatorial explosion where we have to multiply all the types of inputs and all the possible type of outputs, and even all the possible formats for accumulation. So that's a configuration. And so with having so many options, the C++ overloading is very helpful. We're really focusing on C++ API first, but we do understand, and at the end, Fortran and C folks also exist, and so we have ways to handling this combinatorial explosion of naming schemes in a way. But yes, it is not version 1.0 of the standard, and most of the vendor libraries now are very friendly to C++. So other bindings are also planned. So we are looking at Python, of course, Julia, Rust, R, MATLAB, we have folks from MathWorks working with us very closely and incorporating it, so making sure that the standards compatible with where people are doing their computations in their environments. So how to contribute and how to help us? Definitely join the group. Look at the papers, see where we are right now. Drop us an email, and yes, please interact. It's if you think we're not addressing something, definitely open for suggestions. And I just want to mention a few things kind of to show you physically how the C++ looks. We don't really have more time, so I'm just gonna dash through these things really quickly. You will just basically import the Sparseblas namespace, get the matrix created and read it from a file, and then use what we call the view. And so basically we use the library, the implementation would use a view, meaning that you are owning the data, you are responsible for allocating, deallocating it, and all that the library does, it just scans it and computes the results on this value. So that's the semantics of the view. And so the C++ standard, if you look at it, it has this semantics now also embedded in the standard C++ library. So things should look very familiar if you basically live and breathe the C++ library. And it gets complicated when we have to actually do operations. So we talked a little bit about multi-stage operations. So we have to have the multiple matrices. Some of them could be actually an owning interface. When we take the view and we say we want to own it on the library side, so we would create a handle and then go through multiple stages of computation and then resize the views as necessary to make room for new values and then actually perform the operation. So this is how you would be coding these operations. Now, where does the data live? I was mentioned about GPUs. So of course we have to encode that, and we also encode a lot of things. For example, the optimizations. So this is where the C allocators, C++ allocators come in. So you would come in, either we would provide a custom allocator that is GPU specific, optimization specific, and we would basically use this allocator to keep the data in the right place and basically store it in that buffer. So that's the allocator interface. And finally, this is my last slide. This is the multi-stage interface with some memory allocation, and we're trying to pass the optimizations between the stages and do things efficiently. So again, it's very similar, and in some ways it requires this extra effort to unify these vendor interfaces that are kind of diverging. So that's basically what Sparse BLAS is as of today. Thank you very much for having me today.
Thank you very much, Piotr. And let me remind both the people here and the people who are watching us later when this is posted online that we're holding discussion till the end. So I am really looking forward to having a short panel style discussion of all of us in a little bit. But first, we have our last talk in the session, which now is coming from the graph side, more than the linear algebra side. David Bader will talk to us about his project Arachne, an open source interactive graph analytics framework. And so, David, again, if you could take about 25 minutes, and that'll leave us 10 or 15 minutes at the end for discussion. Take it away.
Sure, thanks, John, and welcome everyone to this session. As John mentioned, I'm talking today about Arachne, our open source interactive graph analytics framework for real world problems. And on my title slide are a number of my colleagues at NGIT who have helped build this vision out. So if I get started here, a distinguished professor at New Jersey Institute of Technology and motivated by solving some brain challenges, in massive scale data analytics. I'll go into a few of these different areas during the talk, but we're interested in solving problems coming from areas such as national security, computational neuroscience, and also scientometrics. These are just a few of the areas that we're trying to address where our subject matter experts have massive data sets on the order of terabytes and are trying to analyze those data sets with the challenge that most of the data scientists that we work with, they don't know high performance computing, they don't know how to use the GraphBLAS, they don't know how to program in MATLAB, but they do know Python. And so what we're trying to do is build out a Python interface for solving these massive scale analytic problems, and in particular, the graph analytics. The software that we're building out is called Arachne, and it leverages HPE's Chapel compiler, which is also open source, as well as the Arcuda framework. So Arachne are modules for graph analytics that really sit within Arcuda, an open source framework for data science. We have been funded for the last several years to help build out this framework. And what I pictured here is a user on the lower left of this graphic who is our subject matter expert. And they're just interacting with their Jupyter notebook or with Python. And as easily as they would use NumPy and Pandas or NetworkX for graphs, they're now controlling a Chapel server that is running on the back end, potentially tens of terabytes of data seamlessly for them. So what we're doing at Edge IT is building out what's on the right-hand side of this graphic, namely the parallel algorithms and technologies to make this efficient so that our user who knows just Python is able to manipulate these massive data sets as easily as they could a small spreadsheet on their laptop. So for instance, what happens is we get in data frames. This is very similar to what Jeremy was showing earlier in the talk. We may get tables or other information, maybe from network security. This is our syslogs or the source ID, destination ID of packets that are traveling around the internet. We are able to read in different types of files. And from those data frames, we can induce property graphs. Those are graphs that have labels on the vertices, labels on the edges, and potentially directed edges as well. And once we've converted that tabular data to property graphs, we now can run graph analytics on that graph data structure within Arcuda and Arachne. So on the bottom here, we have a user. This is a sample of real Python code to both ingest massive data and also to do a subgraph extraction and running a few graph analytics at the bottom of the code. What makes this possible is the work that we've been doing. I'll tell you a little bit more about it today. This is also freely available as open source. You can go to GitHub to get Arcuda and Arachne, and the Chapel compiler is also freely available from HPE. As I mentioned, we're interested in several areas of large-scale grand challenge problems. I've mentioned national security, computational neuroscience, and scientometric analysis. Just to go into each one of those very briefly, in national security, we may often be trying to locate a pattern within massive data sets, or we may have a graph where we're trying to run a graph analytic. For instance, a graphic here is representing trying to find high important actors within a network, maybe using an analytic called betweenness centrality. So there are many different types of graph analytics that we wish to run. We have quite a number, probably about a dozen analytics implemented now in Arcuda and Arachne. As an example for doing network packet inspection, we may have these frames, data frames of net flow data, where we have the source and destination IP addresses given, and that induces a graph edge, very similar to what Jeremy showed at the beginning of the session. And those graph edges, then we can send to Arachne and build a graph from it, and then ask questions in the graph domain versus trying to do group bys and joins inside the data frames. We're also working with some collaborators at Harvard University, Jakob Treudel, Hans-Peter Pfister, and Jeff Lichtman, on the analysis of brain connectomes. We're very, very early in this science where now some entire brains can be scanned accurately. For instance, there's an image on the upper right of the complete Drosophila brain of fruit fly with every neuron labeled. And from those images, we can then produce graphs with topology of how neurons connect to other neurons through their synapses and ask questions about how those brains operate. One question that neuroscientists tend to come to us for is solving some hard graph problems like motif finding. A neuroscientist may jot down a little pattern with a couple neurons and the synapses between them. For instance, on the lower right, I have a graphic of a sample of some real patterns, and we're aiming to use Arachne to try to implement subgraph isomorphism or motif finding algorithms to find those patterns. And in most of the patterns that we're given, we can find them in seconds, maybe up to minutes, whereas the de facto standard for doing this problem is the VF2 algorithm implemented in Network X. And in many cases, we're running hundreds, if not thousands of times faster than what can be done in Network X. I'll tell you more about this neuroscience work later in the talk. And also, I mentioned the area of scientometrics. We're funded by the National Science Foundation with Tandy Warnow and George Chaco at University of Illinois to look at new community detection algorithms on networks that contain co-authorship and author interactions to try to answer questions about new and emerging fields of research, who are the experts in a particular discipline, and so on. As I mentioned, this work is supported by the National Science Foundation. We've been very fortunate to receive funding to build out the work here. And anytime I talk about Arcuda, I dedicate the talk to my late colleague, Mike Merrill, who was really one of the visionaries that we worked with in building out Arcuda to what it is today. Arcuda and Arachne use Python for productivity for the user on the front end. And as I mentioned, the HPE Chapel programming language on the back end, which is what we program in, not the user, for that back end heavy lifting. This is an open source compiler built with its origins in a DARPA program about 25 years ago. And the technology has been really fantastic, where we have our students who are new to parallel computing able to write high performant code in the matter of a week, rather than months to become experts in MPI or OpenMP and other such languages. As I mentioned, this Connectome project is quite fascinating to us. We get these massive data sets and are trying to find how the wiring impacts how brains function. And we're working with a great team here, our collaborators at Harvard University. We're also working with the Princeton Neuroscience Institute. Here's an example of one challenge data set. This is a hemibrain data set H01 from Drosophila or fruit fly. It's 1.4 petabytes in size. There's about 57,000 neurons in this data set and about 133 million synapses or connections between those neurons. What we do is we take that data and we convert it into a graph where each neuron becomes a vertex in the graph, and each synapse between two neurons becomes an edge in the graph. The different neurons have types, the different synapses have types. So we're building a very large graph that is a labeled graph or a property graph. And our neuroscientists at this point today can only image about a cubic millimeter of brain tissue. So it'll be a long time till we have a human brain that is imaged. But right now we can look at an entire Drosophila brain or fruit fly, and maybe some small worms and other creatures are being imaged. The patterns that our neuroscientists are interested in are these connectivity motifs that will have signaling between a handful of different neuron types. And we convert those neurons to vertices, the synapses to edges, and look for these labeled graph patterns. So for instance, the tool from Harvard called Momo lets a neuroscientist jot down a little pattern like what I have on the left side of the screen, and we try to correlate that motif connectivity with the neuron morpholog within an actual brain. And there's a tool that we are supporting that allows the neuroscientist to then look at the different locations of that motif in a brain and zoom in on them and try to understand if that pattern is replicated elsewhere in the brain. This is an NP hard problem. However, given the nature of the graph, the fact that we can know the different types in the patterns and different types in the connectome graph itself, we can take theoretic algorithms that solve this hard problem. For instance, Ullman's original algorithm from 2010 using recursive backtracking, or Cordella's algorithm from 2004, VF2, that's inside Network X. And we can improve upon these using heuristics so that for the instances that were given in practice from neuroscientists, we can solve in a couple seconds versus not being able to solve at all. So the graph algorithm is called subgraph isomorphism. We have an original graph and a pattern graph, and we're trying to see if there are copies of that original, of that subgraph in the original graph. This is used in many, many applications, not just in this computational neuroscience, but it's used in bioinformatics, social network analysis, pattern recognition, and many other places. There are quite a number of prior algorithms for this problem. Some are parallel. We look very closely at VF2. This is Cordella's algorithm that's used in Network X. So this has really been the workhorse for most people using subgraph isomorphism. They're running this VF2 algorithm. It basically does the recursive backtracking of Ullman's algorithm, but there's a few improvements to cut corners and have it run faster, to reduce the memory usage, and so on. There's been a number of developments of other algorithms. I won't go through all of these in the time today. There are constraint programming-based solvers, such as the Glasgow subgraph solver from a few years ago, taking a very different approach to try to solve this. And in the last few years, we've seen other both CPU and GPU implementations. For CPU, there's been a parallelization of VF3, the successor to VF2. We'll compare with that a little bit later in the talk. And there's also GPU implementations in Gunrock and a few others. However, our graphs are much, much larger than the GPUs today, so we have to build out our own implementations. Last year, we parallelized VF2 and spoke about it at HPEC 2024. And I won't go through all of the details of that implementation. The graph, the pseudocode is here, and we have a number of improvements or heuristics in order to take candidates and parallelize it across our supercomputer to get VF2 running much faster in parallel. And with that work, we're able to look at this HemmerBrain 1.2 data set and get speedups of about 100-fold over Network X on 128 cores. But today, we're talking in this talk about hypermotif. This is our new parallelization of VF2 that goes beyond what we did last year with VF2 PS. And we're getting some substantial speedups for a variety of problems. We have a couple innovative heuristics and ways to improve the running time. The first is what we call subgraph reordering. We found that if we take a pattern, so for instance, here's a pattern with 4 vertices, and depending on how we number it, the algorithms from VF2, which is in Network X, to VF2 PS, may change their running time orders of magnitude based on that running. In fact, the entries for VF2 that are greater than 16,000 means that we're finished top the time. Running times given instance pattern that we're searching for in a random graph. And you see VF2PS, all of these are running within a minute or so, but the different reordering or how we label the vertices may give us very different running times. So we have a heuristic that will renumber the graph very fast, MBE, and that's been very helpful. We also validation, we have another heuristic called state injection that lets us jump ahead or speed up our computation. We search to time travel to the future to skip unneeded states. And then we have our subgraph matching occurring. So Hypermotif has a few new innovations. We have a paper on arXiv right now that you're welcome to look at that talks about the new innovations in Hypermotif. The pseudocode is really just a wrapper around the VF2PS code that I had on a previous slide. And we do some of the work in these optimizations outside of running VF2PS on the inner core. We compare our experiments on a supercomputer at NGIT. There are a couple different types of nodes. We're using these general nodes, some AMD, modern AMD, EPYC processors, and our running times for this new work are given in the slide. So we took a couple patterns that we created randomly from 3 to 20 vertices. There are 4 bars here. The first bar is Hypermotif running in execution time in seconds. So all of these run in under a minute or so. The next bar next to it is our results from last year, VF2PS. So we're improving upon our running time from last year substantially. The constraint programming-based solver, Glasgow, is this tall yellow bar. And then the bar on the very right is VF3PS. So this is a parallelized version of the improved algorithm VF3 compared to what's in today, Network X, using VF2 that I haven't pictured here. So our algorithms for these problems are substantially faster, orders of magnitude faster than the state of the art today. Here, all of these are running on 128 processors. As I mentioned earlier, the Harvard tool called Momo is using Hypermotif to do subgraph isomorphism or pattern matching. The work has just been accepted at IEEE Viz that will appear in November this year, but the paper is on bioRxiv if you want to take a look. So the neuroscientists will load data and sketch out the patterns they're looking for. We'll run Hypermotif on that graph and patterns, and the Momo tool will visualize the results for the neuroscientist. So we're having quite a huge impact to neuroscience, as this is the tool from Harvard that many groups in neuroscience will use to visualize and search for patterns within connectome graphs. Here's an example of using Momo, where the pattern's drawn in the upper left, and the results give a set of motifs that the user can then tab through and look at the different places where that pattern is found. We ran quite a number of trials for a number of real patterns from neuroscience, and in all cases, our running time is under 5 minutes, but in most it's just a few seconds on real patterns. Compared to Network X, we get up to about 2,000 times faster than what the neuroscientists were doing today. So this is a huge, huge advancement in being able to work through these neuroscience problems. To summarize, in Arachne, I mentioned we have quite a number of graph analytics from connected components and community detection, counting triangles, which is used in clustering coefficient and K-cores. We have K-truss analysis, counting squares, triangle centrality, subgraph isomism, and more. So each one of these algorithms, I've referenced a paper or two where we describe the work. And this is all open source, as I mentioned. The Arcuda framework is available, and the Arachne is the Arcuda modules for graphs, also freely available. We encourage you to download this, to kick the tires on it, to use it on your problems, and let us know how your results are coming along. Again, we published quite a number of papers. The top paper from HPAC 2022 is the main paper that describes Arachne as an Arcuda package. That is the canonical paper on Arachne. And currently we're funded by 3 NSF awards in our lab that I want to acknowledge here. The first one is the core funding for building out Arcuda and Arachne. The second one is our funded work with University of Illinois on scientometrics. And the third one is a brand new project that Quan Liu and I have. She's at Yale, where we're looking at subgraph counting in streaming graphs. I want to recognize my research lab. Some of these folks have recently graduated. Oliver has graduated and joined HPE. Fuhuan just successfully defended his dissertation and will be joining Amazon fairly soon. With that, I'd like to thank you for your attention, and we will hold off questions and move to the panel.
Okay, thank you very much, David, and thank you to everyone. This has been really interesting. Thank you for being patient to hold questions and discussion for the end. So now let me invite everybody, please turn on your video and unmute yourselves. And I will open this up. That includes everyone, and there even a little bit of live audience. So please do join us. And to begin with, I'm just going to ask for someone to kick it off. If people are shy, I've got a few questions myself. But anyone, this is a really amazing range of work in an important general subject area with a lot of very different specific approaches.
Well, John, why don't you kick us off with your questions?
Well, okay. Well, actually, I have just a very specific question, harking all the way back to Jeremy's talk at the beginning, about cybersecurity, which is really cool. I love the idea of multi-billion vertex graphs just sitting there in hypersparse matrices. But it's about the anonymization. Jeremy, you talked about anonymization as obviously a very important aspect of your project, and I just wanted to clarify. The model that you presented at the beginning was sort of a partition of the vertices of the graph or the internet addresses into three sets: the bad guys, the good guys, and everybody else. And does the anonymization try to preserve that partitioning at all, or is that how does that work with anonymization? Is the anonymized work thinking about those three domains or not?
Yes.
Hmm.
So so the person who's providing the data, who has, an anonymization scheme, can also provide anonymized ranges that will reflect those as well. So they can play the same anonymization scheme to essentially the rows that do the anonymization. And so the person analyzing it just sees a 3x3 or 5x5 or whatever set of sub ranges that may be completely unlabeled other than that, right? So you could just get have the data, have, all right, here 4 anonymized sub ranges and do the analysis there. Likewise, you can do the preliminary analysis that then creates statistics for those sub ranges at whoever has the data, and then they're just handing you 3x3 or 5x5 or 20x20 matrices that are just data, right? And so, yeah, so absolutely, it does. That's a big part of it.
Okay, the statistical models of background that you end up deriving, you know, your 5-parameter model. Does that take into account the different subdomains, or I mean, is the background dependent on what subdomain? You know,
Yes, yes. So
what's the relationship there?
so you know, we generally, you know, you want to do you generally start with just analyzing the background for the whole thing first. You need to do that just to make sure the sensor is properly placed. So this is a new concept in the cybersecurity world, but an old concept in the sensing world, that you have to spend a lot of time making sure your sensor is well calibrated. So just
Mhm,
part of the sensing calibration, you do the background of the whole thing. The next step is then you do this range partitioning thing, which is the biggest actual near-term benefit, is it tells you where your cyber sensor is. It may not be commonly known that networks change constantly, and the cyber sensor people are often the last people to be told. And so there's a drift that occurs. And then you want to do the detailed background modeling within each one of those ranges. Like each range should have its own background. Each one of those sub ranges should have its own background model to do
okay.
this more precisely. Yes, and because they do differ quite dramatically. And that's another thing that, you know, we showed, is that one of the big reasons that you have such high false alarm rates in cyber sensors is that, unbeknownst to cyber people, they don't realize they have an implicit prior, which is usually some kind of light tail uniform distribution. So like a
Mhm,
Gaussian distribution is the implicit prior in the statistics they're using,
mhm,
when the data is usually heavy-tailed, and this produces extraordinarily high false alarm rates.
mhm.
Um, it's the equivalent. The false alarm rates are so bad, they're the equivalent of being able to say, "I can guarantee I can lose money in the stock market." Which means, of course, you can make money in the stock market. So it's almost sort of willfully bad. Like you're sort of have to go through random guessing is actually better than using the wrong prior in a statistical analysis. You're better off just random guessing. So
Right.
so this is some of the deeper mathematical stuff, which this audience may appreciate, but most of what I just said is a little bit outside the normal understanding of a typical cybersecurity professional.
Right, right. Yeah, well, thanks. Um, so Piotr, I have a question for you about the sort of standards development process that you're going through. Your work is nobly trying to um, integrate about 30 years of attempts to develop a sparse BLAS standard that could really be considered a standard with you know everything that's going on in industry and vendors and so forth. But specifically, um, you're focusing on C++ for reasons that make a lot of sense as you described, and the I'm curious, you know, the GraphBLAS standard, the first API standard was in C, and Tim's implementation of GraphBLAS follows the C API standard. But there is an ongoing C++ API development effort in on the GraphBLAS side, and I saw on your slide of names at the beginning several of the people who are involved in that. So I'm just curious, to what extent are the Sparseblas standard developers and the GraphBLAS, specifically C++ API developers, to what extent are y'all trying to be coherent, or just be not, you know,
Yeah.
what's
Yeah.
going on?
Yeah, I think I understand the question. And yes, so there's a lot of connections, there's a lot of similarity, there's a lot of junction points, and really it's I would say that whereas one GraphBLAS community is kind of driven by the mathematics and the wider application area, whereas Sparseblas is just simply literally starting at the very bottom. It's just taking those few vendors that have these sparse interfaces, and it's just trying to unify them. But by a vendor, I have to extend that, and and you're sitting next to a vendor of an interface. Basically, Tim's GraphBLAS is we want to actually make that backend as well. So this would basically just join both of these at the hip and just prove how similar and how connected these efforts are. And also, like, I'm not also trying not to take the full credit for the actions, because the effort is actually led by Hartwig Ernst out of the Technische Universität at Munich. So he's basically leading the effort and kind of herding the cats, so to speak. So so yes, I'm just one of the helpers.
Okay, thanks, Piotr.
Yeah, the Sparseblas and GraphBLAS, I'm keen on seeing them, connected better. Say a Sparseblas interface on top of GraphBLAS. There's the two APIs are I think they're complementary. They're serving a different purpose. Sparseblas has things GraphBLAS doesn't have, and GraphBLAS has many things that Sparseblas doesn't have. Like Sparseblas has a field. Well, it's the conventional field, but solving a linear system, you need to divide a triangular system. And we don't have a divide. We have a summering to solve a system. I think you need a field. And so that's something I've thought about adding to GraphBLAS. GraphBLAS could have a notion of a field.
So I have a question for David.
Yeah, go ahead.
So, and this is obviously a set of folks who've collaborated for many years here. And, I started out in the analysis of graph as a rather strict structuralist, interested in the topology of graphs and stuff like that. And at that time, David was really trying to, was a leading thinker in the area of sort of dynamic graphs and streaming graphs. And after sort of plowing the structuralist topological field, particularly these data sets that I've been working on, which turned out to be structurally extremely uninteresting. Like, none of the interesting things that we draw in our graph combinatorics class show up. We just have a bunch of stars, right? And barely even any cliques. And so then I got converted to being a ardent dynamicist, because all the interesting phenomena was in the dynamic behavior. And so I will then ask David, because you showed us a lot of structural things, which is very interesting when dealing with biological systems. And I would be curious to get your thoughts on, well, what are the dynamical aspects, or is it the fact that the data at this point, I mean, they're dealing with, it could be the sensing isn't sufficient yet to do dynamical sensing on these at these types of level. But I'm just curious, what do you envision for the dynamical future for some of this stuff that you're working on?
Dynamics are definitely interesting in the work that we're doing with the connectome, for instance. These are static data sets because it takes literally years to create each data set at the moment. That will speed up in the future. But they are dynamical in that there are new studies that will look at, for instance, different Drosophila at different days of development, or comparing a male versus female Drosophila, where we're looking for change detection between different connectome brains and how they change or develop over time. So in that application space, it's still early for dynamics, but it will get there really, really soon. The software that we have in Arachne and Arachne is really designed for static data sets. As part of the new work that I mentioned with Quan Liu at Yale, we're going to explore and investigate whether we can add more dynamics to Arachne to be able to handle more of these streaming or changing graphs. Today, what we do for dynamic graphs is really look at graph snapshots as they change over time, which is a little bit different from what we did in previous work like Stinger, where our data structure literally had a vertex set, an edge set that could change underneath you as the algorithms ran. So we are somewhere in the middle ground now of trying to understand how to create algorithms for these dynamic problems.
And I have one more question to all of my professorial colleagues, although John is now perhaps not teaching as much, but you know, we in all of the work we've seen the dominance of heavy tail statistics and the true irrelevancy of the Erdos-Renyi random graph, right? And I'm wondering, is there any hope that we will start moving our combinatoric graph theory thoughts and teachings to graphs that are a little bit more connected to the real world? I know Erdos-Renyi is so wonderfully nice toy problem to study, but just to begin to introduce, you know, these distributions that are more relevant, because I do think they dramatically change the way, I mean, the way you think about, you know, combinatoric graph theory. And so I guess for maybe John or David or Tim, do you have any
Well,
thoughts on
let me,
that?
as the most gray-bearded member of the company here, let me hark back to the very early days of sparse direct methods in the say middle late 1970s. Some of the same people who did the first Sparse BLAS standard, John Lewis in particular, and his colleagues at Boeing back then, uh, started the first Harwell-Boeing sparse matrix collection, which became the SuiteSparse collection eventually. And they, at that time, proselytized the idea that a flat random graph or sparse matrix was a lousy model for any kind of real scientific computation, which of course it is for all sorts of reasons. And here we are, 40 years later, still trying to make that argument. So Jeremy, I agree with you completely, and all I can do at this point is hope.
So I agree completely as well, although I was the one talk that used Arachne graphs because for some of these instances, just to do our debugging and testing, it's far easier to try to test on a graph that you can create in place rather than trying to move around large data sets in the testing phase. But I'm guilty of having some Erdos-Renyi graphs in there and completely agree that the more and better graphs to use are available, for instance, in the SuiteSparse matrix collection, in Stanford Graph, Snap Graph collection, and other places, the network analysis and CADA collection as well. So there's many, many graphs, and the real interesting algorithms and heuristics and results come from using those real graphs rather than the artificial ones that we create.
Well, my call to action in the academic community is that within our introductory statistics courses, that there is one lecture on heavy tail distributions as a
Yeah.
start. And you know, and the preface of the lecture should be most of the things that are interesting to you as students, whether it be, you know, natural disasters, pandemics, other types of things, are actually dominated by a set of distributions that we have not studied so far in the class, but that we will now discuss briefly for one lecture. If we could just make that little bit of progress to at least let people know that these things exist, would be a tremendous step forward, right? Because we haven't done that yet. Like you go to any introductory statistics course, and you know, and I always tell people like, well, what's the problem here? It's like, well, you remember maybe in that introduction there was a little footnote that said, you know, IID, you know, things. This book is only relevant to independently identically distributed things that obey the central limit theorem. And within the central limit theorem is the implication that you are only dealing with light tail distributions. And so therefore, the entire book is irrelevant to many of the most important statistical phenomenon that we care about today,
So Jeremy, as in all of science, that kind of change, which seems so simple, is implemented by the passing of generations. And so the hope that I have, Quan Lu at Yale, who's working with David, and her cohort of academics are the people who I think I really do think will implement some of the changes we need. We've reached 8 o'clock, and so I'm going to call this to a close. Thank you all very much. This has been a lot of fun, and it's wonderful to have seen you all, heard all your talks. And SciAm will post the recording of this online in the next day or so that it can be available to an actual audience and going forward. Let me just close though by mentioning that Tim and I are physically here in Montreal at the SciAm annual meeting. One of the aspects of the annual meeting every year is what's called the Ed Block Community Lecture, which is a lecture that's supposed to be interesting and accessible to people beyond the narrow applied mathematicians. And that lecture is this evening at 6:15. It'll be live streamed on YouTube and probably available afterwards. And it's being given by none other than Tim, who will be talking about connections between sparse matrices and art and music. And it's going to be absolutely fascinating. Tim is the only person I know who will actually have given 2 talks at the same SciAm meeting exactly 12 hours apart.
Yes, it will be 12 hours apart.
That's right. So
I have one image in there. One of my artistic images. It's going to look like the Arachne matrix. This is it's a rat's nest, and these beautiful graphs that don't look like that at all.
So on the musical side, you get white noise out of the Arachne graph?
No, I wouldn't even get that. I tried. I think, let's see. Yeah, static would give me Arachne, I think. It just isn't. Yeah, probably. It would just be a balled up wad of paper there.
Yeah.
It's not very pretty. Certainly when you do force-directed graph visualization of an Arachne matrix, you get this big wad of paper, and you don't get anything that shows any structure, any beauty, any regularity or irregularities, or any kind of interesting structure at all. It's just a mess. And no graph is like it.
Okay.
But it is good to break your teeth on, like David said. Break your teeth on an Arachne. Like, if your graph algorithm can handle it, then it can do anything, because it's a mess.
Okay. Thanks again, everybody. We'll close the recording here and hope to see all you virtual folks soon.